Insole construction for articles of footwear. United States Patent Number 4183156, granted on January 15, 1980. Inventor Marion F. Rudy. Application number 058300589, filed on September 6, 1977. Abstract. An improved construction for articles of footwear, such as boots and shoes of all types, includes an inflated insert, preferably in the shape of an insole, having a multiplicity of intercommunicating, gas-containing chambers, and a ventilated moderator member which overlies the inflated insole for evenly distributing the forces exerted by the gas-containing chambers across the plantar surface of the foot of the wearer. The material from which the insole is constructed and the gas contained in the intercommunicating chambers of the insole member are selected so that the rate of diffusion of the gas through the barrier material of the insole will be extremely slow, the insole remaining inflated to a substantial pressure for several years. The pressure to which the intercommunicating gas-containing chambers are inflated is selected so that the insole will support the foot in a comfortable manner, distribute the load on the foot across the plantar portion of the foot, with no unusually high pressure points on the foot, and absorb shock forces experienced during walking, jumping, or running to protect the bones of the foot and body and the various body organs. In addition, energy is absorbed, stored, and returned as motivating energy to the foot, leg, and body in such manner as to make walking, running, and jumping more efficient and less tiring. This application is a continuation in part of application serial number 759429, filed John 14, 1977, now abandoned for improved insole construction for articles of footwear. The present invention relates to inserts, such as insoles, for articles of footwear, and more particularly to an improved inflated insert construction that firmly and comfortably supports the foot of a wearer. Numerous insoles for articles of footwear have been designed in the past in an attempt to provide a comfortable support for the human foot. Many of these proposed prior art insoles have been designed to contain a fluid, either liquid or gas. Gas-filled insoles are shown, for example, in U.S. Patent numbers 900.867, 1006 9001, 1304 915, 1514.468, 1869 257, 2080.469, 2006-45-865, 2006-77, 906, and 3004-69,576. However, none of the prior art fluid-filled insoles has met with any commercial success or substantial use. There are a number of reasons for the lack of success of these prior art insoles. Some of the reasons are as follows. 1. The prior art fluid-filled insoles did not provide adequate support for the foot, thereby causing the foot to constantly hunt for a firm surface in order to maintain body balance. 2. The prior art fluid-filled insoles caused loss of blood circulation in the foot, pinching of nerves, and subsequent numbness in the toes and plantar surfaces of the foot. This was caused by the unconstrained application of fluid pressure against the medial and lateral plantar arteries, veins and nerves, and also the dorsalis pedis and digital arteries, veins and nerves located in the longitudinal arch area of the foot. The prior art fluid-filled insoles were uncomfortable. 4. The prior art fluid-filled insoles were unable to maintain the fluid pressure in the insoles over an extended period of time because the fluid in the insoles would diffuse through the barrier material of which the insoles were constructed. 5. The prior art fluid-filled insoles were difficult to manufacture and relatively expensive. 6. The prior art fluid-filled insoles were not designed properly, at least partially because insufficient consideration was given to the technical structure of the human foot and the manner in which the bones, muscles, arteries, veins, and nerves in the foot move and react during walking, jumping, and running. 7. Fluid-filled insoles inflated to pressures high enough to provide proper support for the feet are, when used by themselves, extremely uncomfortable and irritating to the feet, and may obstruct the flow of blood, bruise tendons, and pinch nerves in the feet. It has been found that one of the reasons for the deficiencies of the prior art fluid-filled insoles is that the pressures of the fluids in the insoles were too low. As a result, during walking, jumping, or running, the fluid in the prior art insoles was pushed away from the high load-bearing areas of the foot, i.e., the heel and ball of the foot, and into areas under the sensitive portions of the foot, i.e., between the ball of the foot and the toes and under the longitudinal arch of the foot, thereby shutting off circulation in these areas. Yet, the pressure of the fluid in these prior art insoles had to be relatively low because if the pressure was too high, the fluid-filled chamber or chambers in the insole would bulge to create a bumpy, irregular, uncomfortable surface. One patent, U.S. Pat. Number 3120,712 suggests that a single chamber bladder be filled to a relatively high pressure of about 30 pounds. However, the single chamber bladder of the U.S. Pat. Number 3120,712 is incapable of supporting the internal working fluid pressure within the confines of the space allowed within the shoe, and it was necessary to provide a chamber between the inner and outer soles of the shoe and a steel plate overlying the bladder to contain it. With the bladder of the U.S. Pat. Number 3120,712 inflated to a pressure of 30 psi, the overlying steel plate must support a force of more than 600 pounds. Accordingly, the steel plate must be extremely rigid and inflexible. As a result, the arrangement of the U.S. Pat. Number 3120,712 will not conform to the plantar surface of the foot and will not be comfortable in use. It has also been proposed to provide flow-restricting connecting passages between fluid-filled chambers in prior art insoles. See, for example, U.S. Pat. Number 2600-239. However, such insoles have been found to be extremely harsh to the foot and do not exhibit a comfortable, floating-on-air sensation for the wearer. Moreover, insoles equipped with flow-restricting passages are impractical from both cost and manufacturing standpoints, due in part to the close and precise tolerances required for the sizes and shapes of the flow-restricting passages. In view of the foregoing, it is an object of the present invention to provide an improved inflated insert or insole construction which will comfortably support the foot of a wearer and which overcomes the deficiencies and disadvantages associated with prior art inserts or insoles. More specific objects of the present invention are as follows. 1. To provide an improved inflated insert or insole construction which distributes the normal forces encountered when walking, jumping, or running over the load-bearing portions of the plantar surface of the foot more uniformly and comfortably. 2. To provide an improved inflated insert or insole construction which expands the normal load-bearing area of the plantar surface of the foot so as to reduce pressure point loading against the foot. 3. To provide an improved inflated insert or insole construction which forms a dynamic, self-contouring, load-supporting surface which automatically and instantly shapes and contours itself to the constantly changing load-bearing plantar surface of the foot. 4. To provide an improved inflated insert or insole construction, which absorbs localized forces, i.e., from stones, irregular terrain, etc., and redistributes these forces away from the localized area and absorbs them throughout the pressurized fluid system of the insert or insole. 5. To provide an improved inflated insert or insole construction which protects the feet, legs, joints, body organs, brain, and circulatory system of the wearer from the damaging shock and vibration forces. 6. To provide an improved inflated insert or insole construction which stores and returns otherwise wasted mechanical energy to the foot and leg in a manner so as to reduce the energy of locomotion consumed in walking, running, and jumping, thereby making these activities easier and less tiring for the wearer. 7. To provide an improved inflated insert or insole construction, wherein the fluid within the insert or insole functions as a working fluid in a system of interconnected fluid chambers which function as fluid springs. 8. To provide an improved inflated insert or insole construction, which is capable of supporting both compression and shear forces. 9. To provide an improved inflated insert or insole construction, which exhibits pre-selected fluid spring rates in one area of the insert or insole substantially different from fluid spring rates in other parts of the insert or insole, and wherein the fluid system in the insert or insole is comprised of a multiplicity of interconnected chambers, and wherein the fluid pressure throughout all of the chambers is nominally the same at any given point in time. 10. To provide an improved inflated insert or insole construction which converts displacement energy of the foot to pressure energy within the insert or insole, and transfers this variable pressure energy to various areas of the insert or insole to provide controlled degrees of support as required in rhythm with the varying need for support during walking, running, or jumping activities of the wearer. 11. To provide an improved inflated insert or insole construction, having fluid-containing chambers in areas underlying the sensitive arch area of the foot, which recede away from contact with the sensitive arch area, allowing the plantar tendons in the arch to move and flex without interference, except during selected portions of the walking or running style when such pressurized chambers move into supportive contact with the arch area. 12. To provide an improved inflated insert or insole construction, which provides essentially permanent, unchanging beneficial characteristics to the foot throughout the life of the article of footwear in which the insert or insole construction is incorporated. 13. To provide an improved inflated insert or insole construction which permits easy adjustment of the level and degree of its functions by merely changing the initial inflation pressure, to thereby permit a single design to be used and optimized to fulfill a wide range of specific footwear applications, i.e., standing, walking, running, jumping, etc. 14. To provide an improved inflated insert or insole construction which, when inflated within a specified pressure range, assumes a precise, predetermined volume, shape, and surface contour in the freestanding, no-load condition. 15. To provide an improved inflated insert or insole construction, which is designed to operate at sufficiently high pressure levels, such that individual fluid chambers within the insert or insole act, in combination with an overlying moderator, to form a complex, interconnected, pneumatic spring system capable of supporting all or a substantial portion of the body weight of the user, and which is of high durability, long life expectancy, and capable of meeting or exceeding typical shoe industry standards and specifications. 16. to provide an improved insert or insole construction inflated to a desired initial fluid pressure and in which the pressure does not drop below its initial value over an extended period, such as a period of several years. More particularly, the fluid pressure automatically increases substantially above the initial value in the early life of the insert or insole. 17. To provide an improved inflatable insert or insole construction, which may be utilized in a new and unique method of fitting a wide range of foot sizes and shapes within a relatively few sizes of articles of footwear. The foregoing and other objects and advantages are realized by the improved insert or insole construction of the present invention, which combines an inflatable insert or insole barrier member of elastomer material, having a multiplicity of preferably intercommunicating, fluid-containing chambers inflated to a relatively high pressure by a gas having a low diffusion rate through the barrier member, the gas being supplemented by ambient air diffusing through the barrier member into the chambers to increase the pressure therein, the pressure remaining at or above its initial value over a period of years. A ventilated moderator bridges the chambers to more uniformly distribute the relatively high load associated with the fluid-containing chambers across the load-bearing portions of the plantar surface of the foot. Numerous other objects and advantages of the present invention will become apparent from the following specification, which, together with the accompanying drawings, describes and illustrates several preferred embodiments of the present invention. Referring to the drawings, Fig. 1 is a top plan view of an embodiment of an inflated insert or insole, embodying the invention, showing in phantom lines a profile of the normal load-bearing portions of the plantar surface of the human foot. Fig. 2 is a top-plan view of a ventilated moderator used in conjunction with the inflated insole of Fig. 1. Fig. 3 is a cross-section taken along the line 3 on Fig. 1 of the metatarsal arch portion of the ball of the foot of a person wearing a shoe containing the inflated insole. Fig. 4 is a cross-section taken along the line 4 of Fig. 1 of the longitudinal arch portion of the foot of a person wearing a shoe containing the inflated insole construction. Fig. 5 is a cross-section taken along the line 5 of Fig. 1 of the heel of the foot of a person wearing a shoe containing the insole. Figs 6 to 9 are cross-sections corresponding to Fig. 4, showing sequential loading of the longitudinal arch portion of the foot on the insole construction. Fig. 6, showing a no-load condition. Fig. 7 is a light load condition. Fig. 8 is a medium load condition, and Fig. 9 a heavy load condition. Figs 10-13 are transverse cross-sections corresponding to Fig. 5, showing sequential loading of the heel on the insole construction, Fig. 10 showing a no-load condition, Fig. 11 a light load condition, Fig. 12 a medium load condition, and Fig. 13 a heavy load condition. Fig. 14 is a top-plan view of the embodiment shown in Fig. 1, modified to include an inflation tube and valve thereon, which may be used in fitting an article of footwear, such as a ski boot, for example, on the foot of the wearer. Fig. 15 is a top-plan view of another embodiment of the invention. Fig. 16 is a top-plan view of yet another embodiment of the invention. Fig. 17 is a top-plan view of the forward portion of a further embodiment of the invention. Fig. 18 is a longitudinal section on an enlarged scale taken along the line 18 of Fig. 17. Fig. 19 is a top-plan view of still another embodiment of the invention. Fig. 20 is a top-plan view of a further embodiment of the invention, with portions cut away. Fig 20A is a longitudinal section taken along the line 20A of Fig 20. Fig 21 is a top plan view of another embodiment of the invention. Fig 22 is a top plan view of yet another embodiment of the invention. Fig 23 is a top plan view of a further embodiment of the invention. Fig 24 is a somewhat diagrammatic top plan view of another embodiment of the invention. Fig 25 is a cross-section taken along the line 25 on Fig 24. Fig 26 is a cross-section taken along the line 26 on Fig 24. Fig 27 is a top plan view of a further embodiment of the invention. Fig 28 is a cross-section taken along the line 28 on Fig 27. Fig 29 is a cross-section taken along the line 29 on Fig 27. Fig 30 is a top plan view of yet another embodiment of the invention. Fig 31 is a cross-section taken along line 31 on Fig 30. Fig 32 is a cross-section through a portion of a shoe, disclosing a modified moderator therein. Fig 33 is a view similar to Fig 32 of another form of the moderator. Fig 34 is a cross-sectional view through the heel portion of the shoe of an inflated insert or insole located within or surrounded by an outer sole, disclosed in a no-load condition. Fig 35 is a view similar to Fig 34 with the heel portion and insert under a loaded condition. Fig 36 is a graph representing the pressure conditions in a typical insole embodying the invention over a period of time. Fig 37 is a graph of the elongation of a film material, from which an insole embodying the invention is made over a time period. Fig 38 is a graph illustrating the advantageous effect of self-pressurization in maintaining a desired pressure in an insole over a period of time. Fig 39 is a graph illustrating the pressure rise of a particular gas over a period of time in a constant volume enclosure and elastic enclosure. Fig 40 is a graph showing the pressure rise of several mixtures of gases over a period of time when confined in a constant volume enclosure and in an elastic enclosure. Fig 41 is a graph showing the percentage growth in diameter for certain chambers in the insole as the fluid pressure in the insole increases. As shown in Figs 1 to 5, an inflated insert 30 in the form of an insole is adapted to be placed in an article of footwear 62, 64, resting upon the outsole 62. The inflated insole 30 comprises two layers 40, 42 of an elastomeric material whose outer perimeters 44 generally conform to the outline of the human foot. The two layers of elastomeric material are sealed to one another, e.g., welded, as by a radio frequency welding operation, around the outer periphery 44 thereof, and are also welded to one another along weld lines 46, 46, 46, and 48, 48. 48 to form a multiplicity of generally longitudinally extending tubular sealed chambers or compartments 50, 50, 50, preferably contoured to parallel the paths of arteries, veins, and tendons in the foot 52, designated by the phantom lines in Fig 1, and to conform to the flow of blood in the foot. The material from which the insole is constructed may be referred to as a barrier material in that it contains a pressurized fluid or gas and forms a fluid barrier to prevent escape of the fluid or gas. The weld lines 46 and 48, which define the tubular chambers. 50 there between terminate at the points 54, 54, 54 and 56, 56, 56, which are located under non-load-bearing areas of the wearer's foot 52, e.g., beneath those portions of the toes T which are connected to the ball of the foot. In Fig. 1, the profile of the normal load-bearing areas of the plantar portion of a wearer's foot 52 is shown in phantom lines. The spaces 55A between the termination points 54, 56 provide intercommunicating passages through which the pressurized fluid can flow freely between the chambers 50, so that the pressure in all chambers is the same at any instant of time. In the embodiment shown in Figs 1 and 3-5, the inside, medial, and outside, lateral tubular chambers 50 are integrally connected to an intermediate tubular section 58, which curves around the rear portion of the inflated insole 30 to cup and underlay the heel H of the wearer. The layers 40-42 are welded to one another at their peripheries 44 to form a sealed barrier member 30, which is inflated by a fluid to cause the intercommunicating chambers 50 to assume their tubular form. The material of the inflated insole 30 and the fluid which fills the chambers 50 are preferably selected so that the fluid will not diffuse significantly through the walls of the insole 30 over an extended period of time, e.g., several years. The insole preferably remaining inflated to support a wearer's foot 52 over a period of time longer than the life of the article of footwear in which the insole is incorporated. The inflated tubular chambers 50 form pneumatic springs, which, in combination with the moderator 32, firmly and comfortably support the wearer's foot as the wearer stands, walks, runs, or jumps. The material from which the inflated insole 30 is constructed should have the following properties. Daru 1. The material should be non-porous such that there are no pinholes, and such that the transport of the fluid which fills the chambers 50 through the material of the insole 30 is restricted to the process of activated diffusion. 2. The material should be elastomeric and capable of stretching within controlled limits to form a complex compound geometric shape without folds and wrinkles. 3. The material should be capable of being easily welded, cemented, or vulcanized to form pressure-tight, high-strength seams, e.g., weld lines 46, which define the fluid-containing chambers 50. 4. The material should be highly resistant to flexural fatigue. 5. The material should be highly resistant to fungi and perspiration typical of the environment within the shoe or other article of footwear in which the improved insole construction is incorporated. 6. The material should not contain plasticizers or other materials that would migrate from the material in service and cause toxic reactions with the skin, degradation of the properties of the material, or damage to adjacent parts of the article of footwear in which the insole is incorporated. 7. The material should have excellent resistance to relaxation and stress when subjected to continuously high tensile forces. 8. The material should have excellent elastic deformation and recovery characteristics without permanent set. 9. The material should maintain the above characteristics within a temperature range of between about 30 degrees or F. 10. The material should have ample strength to withstand the inflation pressures and operating pressures and conditions within the chambers 50 without damage to the material. It has been found that the material of the insole should be selected from the following material: polyurethane, polyester elastomer, e.g. Hetrel, fluoroelastomer, e.g. Viton, chlorinated polyethylene, CPE, polyvinyl chloride, PVC, with special plasticizers, chlorosulfonated polyethylene, e.g. Hypalon, polyethylene, ethylene vinyl acetate, EVA, copolymer, e.g., ultrathane, neoprene, butadiene, acrylonitrile rubber, BUNA-N, butadiene styrene rubber, IG, SBR, GRS, BUNA-S, ethylene propylene polymer, e.g., Nordel, natural rubber, high-strength silicone rubber, polyethylene, low density, adduct rubber, sulfide rubber, methyl rubber, thermoplastic rubbers, e.g., Creighton. One material which has been found to be particularly useful in manufacturing the inflated insole of the present invention is cast or extruded ether-base polyurethane film having a Shore A durometer hardness in the range of 80 to 95, e.g., J.P. Stevens's film MP1AE or MP18990AE, natural unpigmented in color. The physical properties of the selected insole materials, including tensile strength, modulus of elasticity, fatigue resistance, and heat sealability, are very important in a product as the insole which is subjected to an extremely demanding duty cycle when worn in a shoe for the life of the shoe. The average person walks approximately 2 to 3 miles per day, which approaches 1,000 miles per year. Assuming 1,000 paces to the mile, the insole encounters 1,000 cycles per year. Each of these cycles compresses the insole to about 25% of its freestanding inflated height. Therefore, the insole, including the critical areas along the edges of the weld areas, is subjected to a potentially very destructive accumulation of peak stress and stress reversals. The selected materials provide the best possible endurance under these conditions. Also, and equally important, the design configurations of Figs 1 to 31 are such as to minimize stress concentrations and minimize the overall stress levels on the welds, even at a maximum design 50 psi condition, so as to give the insole long in-service life in excess of the life of the shoe. Long life has been proven by 5 years of extensive testing, both in actual in-shoe tests as well as in testing machines, which simulate the duty cycle to greatly accelerated schedules. The material of the insole may be reinforced with cloth or fibers, and may be laminated with other materials to achieve better overall characteristics. The thickness of the material of the inflated insole should be between about 0.01 and about 0.050 of an inch. The fluid which fills the pressurized chambers 50 of the inflated insole should preferably be a gas which will not diffuse appreciably through the walls of the insole material for an extended period of time, e.g., several years. The two most desirable gases have been found to be hexafluorothane, e.g., Freon F116, and sulfur hexafluoride. Other gases which have been found to be acceptable, although not as good as hexafluoroethane and sulfur hexafluoride, are as follows: perfluoropropane, perfluorobutane, perfluoropentane, perfluorohexane, perfluoroheptane, octafluorocyclobutane, perfluorocyclobutane, hexafluoropropylene, tetrafluoromethane, e.g. freon F14, monochloropentafluoroethane, e.g. freon F115, 1,2-dichlorotetrafluoroethane, e.g. freon 114, 1,1,2-trichloro 1,2,2-trifluoroethane, e.g. freon 113, chlorotrifluoroethylene, e.g. genetron 1113, bromotrifluoromethane, e.g. freon 13B1, and monochlorotrifluoromethane, e.g. freon 13. The foregoing gases may be termed supergases because of their unique characteristic, i.e., their unusually low diffusion rates through the elastomeric barrier material of the insert or insole. The inflation characteristics of a supergas, hexafluoroethane, Freon F116 in a typical insole are shown in Fig 36. This is a relatively high-pressure insole for use in athletic activities. The material is Stevens MP 1890 AE urethane film, 0.020 inches thickness, with inflation using 100% supergas, F116, at an initial pressure of 34.7 psia, 20 psig. As seen in Fig 36 Curve 1, the pressure within the enclosure rises about 4 to 5 psi during the first 2 to 4 months, and then very gradually declines during the next 2 years. At the end of 2 years, the pressure is still somewhat higher than the initial inflation pressure. Over a 5-year period, many long-term pressurization tests were conducted with the various supergases in elastomeric enclosures. They all exhibited this phenomenon of self-pressurization, or self-inflation, where a substantial pressure rise of 4 to 8 psi occurred during the first several months. In some cases, the pressure rise was as high as 11 to 12 psi. The selected elastomeric films used in the insole are not good barrier materials, low permeability, for air and most gases, as are films made from such materials as mylar, saran, PVDC, and metal foil. The important properties for the insole film, which are listed above, do not include the requirement that the film be made from any of these typical barrier-type materials in order to achieve these remarkably low rates of gaseous diffusion. Therefore, as compared to most materials classified as barriers, the material of the insole is relatively quite permeable to most gases, vapors, including the primary constituents of air, i.e., N2 and O2. Only the special group of gases, vapors, which are defined herein as supergases, exhibit very low diffusion rates through these films. These supergas diffusion rates are extremely low, as is seen in Curve 2 of Fig 36, which is the curve for the partial pressure of Freon, F116, in a constant volume urethane enclosure. After 2 years, the partial pressure of the supergas is still as high as 80 to 90% of the initial starting partial pressure. On the other hand, the N2 and O2 gases of the natural air environment surrounding the insole diffuse fairly rapidly into the enclosed volume until the partial pressures of these gases within the volume equals the partial pressures which exist outside the enclosure in the natural atmosphere, i.e., N2 ha 11.26 psia and O2 94 psia. This is highlighted in Curve 3 of Fig 36, which gives the trend of total pressure, which is made up of N2, O2, and supergas, within an urethane enclosure for the case of constant volume. For this case, a large pressure rise occurs, approaching 14.7 psi. The difference between the two total pressure curves 1 and 3 is due to the stretching of the envelope under pressure, with the insole volume, curve 1, expanding as a function of time. The insoles are designed so that the film stretches, due both to elastic deformation and permanent set resulting from tensile relaxation, an appropriate amount so as to mitigate a portion of the self-pressurization pressure rise. The control of volume growth is obtained through appropriate matching of 3 design parameters, i.e., modulus of elasticity of the material, thickness of the material, and the overall stress level. The stress level is a function of the type of insole pattern, i.e., tubes, Figs 1 and 16, or dots, Figs 17, 20, 21, 22, and the geometric size of the air passages. Excessive pressure rise is detrimental to the proper functioning of the insole. It should operate within a range of pressure plus 20 to plus 25% of the average gauge pressure selected to match the requirements of the specific application, i.e., high pressure for strenuous athletic activities, lower pressure for less active sports, and still lower pressures for walking, standing, etc. The objective of the predetermined and programmed volume growth is to have the pressure at the end of the self-pressurization period be at the top of the range of optimum pressure, i.e., about 20 to 25% above the initial starting pressure. In this way, the maximum permanent inflation life of the insole is achieved. The slow decline in pressure due to supergas diffusion can occur over the maximum possible range of pressures, i.e., from the top of the desirable pressure range to the bottom of the pressure range. Therefore, self-pressurization contributes to permanent inflation in three ways. 1. Adds pressurization energy to the system during the self-pressurization period. 2. Raises the pressure from the initial inflation pressure, the midpoint in the range of optimum pressures, to the top of the range of optimum pressure. 3. Stores fluid pressure energy in the film as elastic deformation. This energy is then recovered as fluid pressure is lost in the system and the film contracts, reducing the internal volume and tending to maintain a more constant, uniform internal fluid pressure. Starting at the top of the pressure range prolongs to a maximum extent the time period during which the loss of pressure due to supergas diffusion can act before the pressure ultimately drops below the bottom of the band of optimum pressures. This design feature is illustrated further in Fig 37. In this graph, the rate of elongation of urethane film, based on suspending weights on test strips of film, is plotted as a function of time, curves 1. Also plotted on the same time scale is the pressurized trend of the self-pressurization phenomenon, curve 2. As is seen, the two time-phased characteristics are similar in that one offsets the other. They also become asymptotic at about the same time. In order to highlight the importance of self-pressurization in adding pressure energy to the system, curve 1 of Fig 36, total pressure within an expanding volume insole envelope, is replotted on a gauge pressure scale as curve 1 Fig 38. Also plotted as curve 2 is the partial pressure of hexafluorethane supergas, F116, within the same expanding volume. The contribution to total pressure added by self-pressurization is indicated by the area which lies between the F116 partial pressure curve 2 and the total pressure curve 1. Self-pressurization adds an increment of 14.7 psi pressure to the 100% supergas system, essentially irrespective of the initial starting pressure of the supergas. This is a large and influential increment for devices like the insole, which operate at pressure levels from 2 to 40 pseg. For example, in the Fig 38 example, even with an expanding envelope, the total pressure, curve 1, remains above the initial starting pressure after 2 years. Were it not for self-pressurization, however, the pressure would have dropped to 37%, 71.3 psig, of the initial pressure, supergas partial pressure curve 2. Two more pertinent comments can be made regarding the phenomenon of self-pressurization and Fig 38. First, self-pressurization causes a maximum amount of air to diffuse inwardly into the inflated device. Therefore, for a given desired total pressure, air plus supergas, a minimum partial pressure of supergas is required. Because the supergas pressure is at its lowest value, it will diffuse out at its slowest possible rate. This helps maintain long-term pressurization at a relatively constant value. The air within the enclosure will, of course, not diffuse out at all, because the internal partial pressure is the same as the outside partial pressure of the air of the ambient atmospheric environment. Thus, the situation of having maximum air and minimum supergas within the enclosure for a given desired total pressure is the ideal situation for long-term constant pressurization and permanent inflation. The second comment concerns the application of external loads to the inflated insole. When load is applied, the internal pressure of both air and supergas rises. Air pressure rises above the outside air pressure, and therefore some of the air will be forced to slowly diffuse out. Essentially, no supergas will diffuse out unless heavy loads are applied for extremely long periods of time. When the load is removed, the device will reinflate itself again back up to the original working pressure through the mechanism of self-inflation. This self-inflation feature works effectively for a device like an inflated insole. The inflated insole has an ideal duty cycle in that the load is applied about half the time when the shoes are in use during the day, and the load is removed about half the time when the shoes are removed at night and when the wearer is sitting down while the shoes are in use. Thus, the insoles cyclically reinflate themselves to make up for the slight loss in air pressure, which can occur during the periods of use. A similar situation occurs when the insoles are taken to high altitudes, as within a suitcase in an airplane. Again, some air will temporarily be forced to diffuse out, but the air will reinflate back into the insoles when the shoes are returned to lower altitudes. This self-compensation effect with load and altitude changes is an important feature of the inflated insole. The effect of self-pressurization is even more striking when enclosures are inflated to low initial pressure, 2 psig, as in the case of inflated insoles used in street shoes for walking and standing and for orthopedic purposes. In Fig 39, Curve 1 plots the pressure rise as an insole made from thin, 0.010 lower modulus of elasticity, urethane film, Stevens MP 1880. When this insole was inflated to an initial pressure of 2.00 psig with 100% supergas, the pressure rose to many times the initial pressure, with the final pressure reaching 3.7 times the initial pressure after approximately 6 weeks. This large pressure rise occurred even though the low modulus film stretched considerably under pressure and the internal volume of the insole increased about 40%. The large excursion from the 2.0 psig design pressure level is not desirable. Not only does the cushion get too firm to perform properly, but its thickness increases to such an extent that there is inadequate room for the foot in the shoe. In low-pressure enclosures, therefore, the percent pressure rise over the initial starting pressure can be very large. For instance, Fig 39 also illustrates the present pressure rise with a constant volume enclosure for several cases of initial inflation gauge pressure, i.e. 0, 2.0 psig, 7 psig, and 12 psig. The graph indicates, as mentioned, the insole made from 0.010-inch methane film, Stevens MP 1880 film, is shown to rise in pressure only 3.7 times because the volume increased approximately 40% during the time period. Had the volume been constant, it would have risen 8.1 times. It is obvious that the achievement of an acceptably constant pressure in a low-pressure insole was not possible using 100% supergas. Even if the initial inflation gauge pressure was 0, the pressure rise would be in the order of 5 to 6 psi. To prevent overpressurizing of the insoles, mixtures of air and supergas were used as the initial inflation medium. Fig 40 plots the self-pressurization pressure rise for several mixtures of supergas and air. The graph indicates assuming a constant volume enclosure at an initial pressure at 2.0 psig. Also shown as curve 1 in Fig 40 is the pressure rise with an insole made from 0.010 MP 1880 film. With tensile relaxation, the pressure only rises from 2.0 to 2.4 psig. The corresponding volume increase is 10 to 11%. This is acceptable within the definition of a constant pressure insole. Thus, it can be concluded that mixtures of air and supergases can be used to achieve a long-life insole operating at low levels of constant pressure. A further approach is to initially inflate to a very low pressure, 0 psig supergas, so that the enclosure is just barely distended, low volume to surface ratio. As reverse diffusion occurs, the enclosure distends further until the maximum volume to surface ratio condition is reached, still with zero tensile stress in the film. This volume change drops the partial pressure of the supergas and mitigates the subsequent self-pressurization pressure rise. However, even for this case, mixtures of air and supergas are probably required in many cases to prevent excessive pressure overshoot. Returning to Fig 1 and related figures, the insole 30 is inflated and pressurized with a supergas, or another fluid such as air or liquid, for example, after the two layers 40-42 of the elastomeric material have been welded around the outer periphery, 44 thereof, and along the weld lines 46-48 to form the multiple chamber 50 construction shown in Figs 1 and 3.5. Inflation may be accomplished by inserting a hypodermic needle into one of the intercommunicating chambers 50 and connecting the needle to a source of pressurized fluid. After inflation, the hole created by the needle is sealed. The pressure to which the chambers 50 of the insole 30 are inflated is most important. The pressure in the intercommunicating chambers 50 must be high enough to perform a supporting function for the foot, to distribute the load on the foot more uniformly across the ball-bearing plantar portion of the foot, so that there are no unusually high pressure points thereon. Yet, the pressure to which the insole 30 is inflated must be low enough so that the insole is comfortable to the wearer and will perform a shock-absorbing function to protect the bones of the foot and body and the various body organs against shock forces which occur when the wearer is walking or running. More specifically, the intercommunicating chambers in the insole 30 should be inflated to such a pressure that the inflation fluid performs the following functions. 1. Distributes the normal forces associated with standing, walking, running, and jumping over the load-bearing portions of the plantar surface of the foot in a relatively uniform and comfortable manner. 2. Expands the normal load-bearing area of the plantar surface of the foot, thereby reducing the pounds per square inch loading on the foot. 3. Creates a dynamic, self-contouring, load-supportive surface, which automatically and instantly shapes and contours itself to the constantly changing load-bearing area of the plantar surface of the foot. 4. Absorbs localized forces, e.g. from stones, irregular terrain, etc., and redistributes these forces away from the localized area and absorbs them throughout the pressurized fluid system of the intercommunicating chambers. 50. 5. Protects the feet, legs, joints, body, organs, brain, and circulatory system of the wearer from damaging shock and vibration forces. 6. Stores and returns otherwise wasted mechanical energy to the foot and leg in a manner so as to reduce the energy of locomotion consumed in walking, running, and jumping, thereby making these activities easier and less tiring for the wearer. In this regard, it should be noted that the improved inflated insole of the present invention works in concert with the natural articulated pendulum motion of the feet and legs to make walking, running, and jumping easier and less tiring. Displacement energy is absorbed from the foot by the inflated insole as the foot makes initial pressure contact with the ground. This energy is converted to fluid pressure energy and stored temporarily within the inflated insole while simultaneously performing important support functions. As the foot reaches the end of its stride, when walking or running, this fluid pressure is converted back into energy of motion, assisting the foot and leg muscles in lifting the foot from the ground and swinging it forward as a pendulum into the next stride. Experienced and highly disciplined marathon runners have reported substantial improvements in speed, endurance, and comfort with a concurrent reduction in pulse and respiration when testing the improved insole construction of the present invention as compared to running the same identical course in shoes without the insole construction of the present invention. 7. Function as a working fluid in a complex system of intercommunicating fluid-containing chambers. 8. Shape the barrier material of the insole into three-dimensional fluid-containing chambers of specific sizes and shapes which are capable of a. Supporting both compression and shear forces, and b. Exhibiting pre-selected spring rates in one area of the insole, substantially different from spring rates in other parts of the insole. 9. Convert displacement energy of the foot to pressure energy within the insole and transfer this variable pressure energy to selected areas of the foot, e.g., the longitudinal arch and the metatarsal arch. It has been found that the foregoing functions are performed if the insole of the present invention is inflated to a pressure of between about 2 psi and about 50 psi. Of course, the use of the article of footwear in which the improved insole construction of the present invention is incorporated will determine the optimum pressure to which the insole should be inflated. For example, if the insole is to be employed in a pair of track shoes for a runner, the insole should be inflated to a higher pressure than if the insole construction is to be employed in a pair of ordinary street shoes. For low-level athletic endeavors, e.g., jogging, the pressure to which the chambers of the insole should be inflated is between about 8 and 18 psi. For high-level athletic endeavors, the inflation pressure should be between about 15 and 30 psi. For ordinary street shoes, the inflation pressure should be between about 2 and 12 psi. As shown in Figs 1 and 3-5, the top surface of the inflated insole 30 has a number of peaks, at approximately the longitudinal center line of each of the tubular chambers 50, and valleys, the areas adjacent the seam lines 46 and 48, which may be uncomfortable to stand, walk, run, or jump on. To eliminate such discomfort, to more uniformly spread the pressure associated with the inflated chambers 50 across the plantar surface of the wearer's foot, and to provide ventilation, the present invention contemplates the use of the ventilated moderator 32, Fig 2, to overlie the insole 30. The moderator 32 consists of a sheet of semi-flexible material whose outer perimeter is in the general shape of the outline of the human foot. The moderator 32 is preferably, but not necessarily, provided with a plurality of openings or holes, 60 extending therethrough. Although not specifically shown in the drawings, it is contemplated that it may be desirable to provide the holes 60 in the moderator in a pattern wherein the holes will parallel the weld lines 46 and 48 in the insole 30 to promote better ventilation around the foot of the wearer. As best shown in Figs 3-5, the moderator 32 bridges the inflated tubular chambers 50 to comfort the foot of the wearer by more uniformly distributing the relative high loads associated with the fluid-containing chambers across the load-bearing portions of the plantar surface of the foot. The moderator 32 is semi-flexible, in that it must be flexible enough to conform to the dynamic, i.e., changing contours of the plantar, i.e., bottom surface of the wearer's foot. Yet, the moderator 32 must be rigid enough to bridge the tubular chambers 50. The holes 60 in the moderator 32 permit air from between the moderator and the inflated insole 30 to circulate around the foot of the wearer as the insole is compressed under the load of the foot. As noted above, to facilitate this function, the holes 60 are preferably arranged in a pattern such that the holes parallel and overlie the seam lines 46 and 48 of the insole 30. As best shown in Figs 3 to 5, the moderator 32 overlies the inflated insole 30. Although not shown in the drawings, it is contemplated that the moderator 32 may be secured, e.g. sewn, glued, or otherwise secured, to the article of footwear in which the improved insole construction of the present invention is incorporated. This may be accomplished by securing the outer peripheral edge of the moderator 32 either to the sole 62 of the footwear, Figs 3-5, or between the shoe upper 64 and the sole. It is also contemplated that the moderator 32 may be an integral part of the footwear in which the insole construction of the present invention is incorporated, in which case the inflated insole 30 would be inserted into a space or cavity provided in the sole and or heel of the footwear beneath the moderator 32, Figs 34-35. The inflated insole 30 may be inserted into such space in the sole of the footwear during manufacture of the footwear or after manufacture. In this configuration, as the fluid springs in the insole compress and expand under a changing load, the vertical displacement of the insole may be confined predominantly within the sole and or heel of the shoe. The foot, shoe upper, and the moderator would then move together, in unison, to achieve a higher degree of lateral support than would be possible with the inflated insole-moderator combination installed on top of the sole and or heel of the shoe. While it is contemplated that numerous materials may be employed in making the moderator 32 of the improved insole construction of the present invention, several materials have been found to be particularly suitable, i.e., polypropylene, polyethylene, polypropylene, ethylene, vinyl acetate copolymer, e.g., Profax SB 814, and polyethylene ethylene vinyl acetate copolymer, e.g., Ultrathane 630. Other acceptable materials include Texan and similar materials. The thickness of the moderator may be between about 0.005 and 0.080 of an inch. It has been found that it may be desirable to cover the top surface, i.e., that surface which will contact the foot of the wearer, of the moderator 32 with a relatively thin, e.g. between about 0.002 and 0.020 of an inch, layer of leather, cloth, or a deformable material, such as foam, to provide additional comfort. Figs 3 to 5 are transverse cross-sectional views taken through the metatarsal arch portion 34, the longitudinal arch portion 36, and the heel 38, respectively, of the foot of a person wearing an article of footwear equipped with the improved insole construction of the present invention. As shown in Figs 3 to 5, the inflated insole 30 is positioned in the bottom of the footwear between the sole 62 of the footwear and the wearer's foot. The ventilated moderator 32 overlies the inflated insole to bridge the inflated chambers 50 to more uniformly distribute the load across the plantar surface of the foot. Figs 3-5 illustrate the condition of the improved insole construction of the present invention, i.e., the inflated insole 30 and the moderator 32, when there is no load on the insole, e.g., when the wearer is seated. The inflated tubular chambers 50 exert substantially no load on any portion of the foot. Figs 6-9 illustrate in sequential form the progressive loading on the longitudinal arch portion 36 of the foot of a wearer of the improved insole construction of the present invention, and the supportive function performed by the improved insole construction during walking. As shown in Fig 6, under no load conditions, i.e., when there is substantially no weight on the foot, only the outermost, i.e., lateral portion of the longitudinal arch 36 is in contact with the moderator 32. As shown in Figs 7, 8, and 9, as the wearer walks, the longitudinal arch portion 36 of his foot moves from a supinated position, Fig 7, to a pronated position, Figs 8 and 9, wherein the full load of the body is exerted over the entire load-bearing area of the foot and the navicular bone, not shown. In the longitudinal arch portion, 36 of the foot tends to roll inwardly. As this occurs, as shown in Fig 8, the inner, sensitive portion of the longitudinal arch 36 makes contact with the improved insole construction of the present invention, the insole construction providing a pronounced arch supporting force. As additional force is exerted on the inflated insole 30, as shown in Fig 9, the volume in the tubular chambers 50 under the normal load-bearing area of the foot decreases to increase the working pressure throughout all of chambers 50 by as much as 50 to 100% or greater. In other words, the total fluid pressure in the tubular chambers 50 increases due to the decrease in volume. This increased fluid pressure causes the adjacent, larger, more highly stressed chambers, which are in a semi-rigid elastic state, to expand and grow noticeably larger in diameter, thereby 1. Filling in the space under the longitudinal arch 36, 2. Bringing the moderator 32 into supportive contact with the longitudinal arch, and 3. Arresting and reversing downward and rotational movement of the longitudinal arch and navicular bone of the foot. The other smaller chambers which operate at lower levels of stress are of such size and shape as to be substantially rigid, constant size and diameter, when subjected to the maximum pressures which occur within the insole. The rigid and semi-rigid, elastic modes of operation are explained further in Fig 41. The 5 curves on the right-hand side of the figure indicate the percentage growth in diameter for chambers A, B, C, D, and E as a function of internal pressure level. On the left-hand side of the figure, a diagrammatic representation of the geometry of the chambers is shown for several different levels of pressure, e.g. 0, 71.2, 15, and 25 psi-GE. To assist the explanation, in this figure the chambers are shown in the freestanding condition, as they would appear with no external loading. At zero pressure, of course, all chambers are essentially flat. At 71-2 psi, all the chambers have been rounded out to circular shape. However, at this pressure, the elastomeric material, although under stress, has not yet been stretched or elongated any significant amount in any of the chambers. Pressures higher than 71.2 psi-G correspond to pressure fluctuations caused by total insole volume changes due to application of external loads, as explained above. At 15 psi, the larger chambers D and E, which are the most highly stressed, have started to elastically expand, stretch, to larger diameters. At this pressure, these chambers DE are said to be operating in the semi-rigid, elastic mode. Because the smaller chambers A, B, and C are under less stress, they have not stretched and their diameters are essentially unchanged. These smaller chambers are said to be operating in the rigid mode. At still higher pressures, 25 psig, the largest chambers D and E have continued to expand at an ever faster rate. Intermediate-sized chamber C has started to elongate. Chambers A and B, however, are still operating in the rigid mode at constant diameter. The curves A, B, C, D, and E on the right-hand side of the figure also illustrate the characteristics of rigid and semi-rigid operation. At low internal pressures, all the curves for all the tubes are vertical. For this case, growth in chamber diameter with increasing pressure is essentially zero. Thus, the vertical portions of curves A, B, C, D, and E corresponds to rigid mode operation. At higher pressures, the curves for the larger chambers D and E start to bend to the right, indicating an increase in diameter, with the largest chamber E expanding the most. At maximum working pressure, 25 psig, small chambers A and B are still on the vertical portion of their curves. However, the diameters of the larger tubes C, D, and E have expanded, with the largest tubes D and E having expanded significantly. If the internal pressure is increased to levels significantly in excess of maximum working pressure, the tubes will, of course, expand even further. At very high pressures, the largest chambers can be forced to stress levels which exceed the elastic limit of the material. This is indicated as ballooning in the figure and can result in loss of pressure and/or rupture of the material. As the curves indicate, however, a margin of safety is designed and built into the insoles so that the maximum expected working pressure is well below those pressures which would cause the tubes to approach their elastic limits. The margin of safety is more than sufficient to guard against such factors as excessive heat in the shoes, high-altitude effects, etc. The large volume increase in the system as it approaches the ballooning condition creates a highly effective self-stabilization characteristic. By this method, excessively high fluid pressures resulting from service, heat, altitude, etc. are self-correcting so as to enhance the overall service life of the product. It should be noted that one of the advantages of the present invention is that the improved insole construction does not make contact with the inside, medial, and central portions of the longitudinal arch when there is no substantial load on the foot, Fig. 6. This allows the tendons which extend longitudinally through the foot to move and flex freely in the longitudinal arch portion so that there is no resultant irritation of these tendons, a feature which is particularly important during the end portion or toe-off phase of the stride of the wearer. Figs 10 to 13 are sequential transverse cross-sectional views taken through the heel of a wearer to show how the improved insole construction of the present invention cups the heel and provides a shock-absorbing function as weight is progressively put on the heel. As shown in Figs 10 to 13, as weight is progressively put on the heel of the foot, the inflated tubular chambers 50 in the inflated insole 30 are compressed to decrease the volume therein and thereby increase the pressure of the gas contained therein. As the tubular chambers 50 are depressed under the load of the body, these chambers 50 will deflect so as to absorb pressure spikes and thereby protect the various parts, e.g., bones, organs, etc., of the wearer's body. As noted above, the embodiment of the inflated insole 30 of the present invention shown in Fig. 1 has its inside and outside tubular chambers, 50-50, integrally connected to one another through a rear tubular chamber 58, which encircles the rear of the wearer's heel to cup the heel. While this rear tubular section 58 adds comfort and support to the wearer, it does tend to make the rear portion of the inflated insole 30 curl somewhat. Fig 15 shows another embodiment of an inflated insert or insole 130 of the present invention, wherein the inside and outside tubular chambers 150 do not have an interconnecting tubular section which encircles the wearer's heel. The inflated insole 130 includes a plurality of longitudinally extending tubular chambers 150, which are defined by generally longitudinally extending weld lines 146, and 148. As in the case of the inflated insole 30 shown in the embodiment of Fig 15, is formed by welding two sheets of a suitable material, e.g. polyurethane, along a peripheral seam 144 and weld lines 146, and 148, which terminate at weld termination points 154, spaced from weld termination points 156, respectively, to provide spaces 155A for passage of fluid between chambers. As in the case of the embodiment of Fig 1, welding of the two sheets of polyurethane of the inflated insole 130 may be carried out through a conventional radio frequency welding operation. A ventilated moderator 32 overlies the inflated insole 130 to more uniformly distribute the load forces imposed by the inflated insole 130 across the planar surface of the wearer's foot. Since the tubular chambers 150 in the inflated insole 130 shown in Fig 15 are generally longitudinally extending, the inflated insole 130 will lie relatively flat after inflation and pressurization to facilitate ease in handling and storing of the insole, and subsequent insertion and securing of the insole construction within an article of footwear. Fig 16 shows another embodiment of an inflated insert or insole 230 of the present invention, wherein, like the insole 30 of the embodiment shown in Fig 1, the inside and outside tubular chambers 250 extend rearwardly into a rear tubular chamber 258, which encircles and supports the rear portion of the heel of the wearer. In addition, the forward portions of the longitudinally extending tubular chambers 250 extend into forward curved tubular chambers 260, which encircle the forward portion of the ball of the foot and the toes of the wearer to provide additional support beneath these portions of the foot. As is the case with all of the embodiments of the inflated inserts or insoles, the insole 230 is adapted to be employed in conjunction with a ventilated moderator 32, which overlies the insole to more uniformly distribute across the plantar surface of the wearer's foot the forces imposed on the foot by the inflated insole. It has been found that the insole construction of the Fig 16 embodiment 230 provides an unusually high degree of comfort to the wearer. Fig 17 and 18 illustrate another embodiment of an inflated insert or insole 330. In the inflated insole 330, the two layers 340 and 342 of barrier material, e.g. polyurethane, from which the insole is constructed, are welded together at a plurality of generally circular weld areas, 346. As shown in Fig 17, the weld areas 346 of the inflated insole 330 are preferably arranged in triangular patterns with each weld area 346, forming an apex of an equilateral triangle, as shown in Figs 17 and 18, with no load on the inflated insole 330. The inflated areas of the insole make contact with the overlying ventilated moderator 32 and the underlying sole 62 at 6 points 345, 345 around each weld area 346. These 6 points of contact, 345, form a relatively smooth supporting ring around each of the circular weld areas, 346. Thus, each weld area, 346, is surrounded by an annular chamber, and the inflated insole 330 is comprised of a multiplicity of generally annular intercommunicating chambers. The insole construction 330 shown in Figs 17 and 18 tends to lie flat rather than curl. In addition, the inflated insole construction shown in Figs 17 and 18 picks up and supports load, i.e., the weight of the wearer, with less deflection, and, as a result, provides more firm support with excellent shock-absorbing characteristics. In addition, the insole 330, as well as the insoles disclosed in Figs 1923, described below, transfers shear forces between the upper and lower layers 340 and 342 in an excellent manner, thereby minimizing lateral and forward movement of the foot relative to the sole 62 of the footwear in which the insole construction is incorporated. Fig 19 illustrates another embodiment of the invention, wherein inserts in the form of inflated PEDs 430 and 431, which are designed to be inserted beneath the ball and heel, respectively, of a wearer's foot, rather than a full-length insert or insole, which spans the entire plantar surface of the foot. Like the inflated insert or insole of Figs 17 and 18, the PEDs 430 and 431 are comprised of 2 layers of suitable material, e.g., polyurethane, welded together around their peripheries 443 and 444, and at a plurality of weld areas 446, 446. 446 arranged in triangular patterns. Although not specifically illustrated in the drawings, it is also contemplated that the 2 layers of material from which the inflated PEDs 430 and 431 are made may be secured together along weld lines to form longitudinally extending tubular chambers, like the chambers 50 in the insole 30 shown in Figs 1 and 3.5. Inflated PEDs, such as PEDs 430 and 431 shown in Fig 19, are less costly to manufacture than a full-length insert or insole, and can be inflated to different pressures to provide different levels of support between those portions of the foot under which the PEDs are placed. In addition, PEDs take up less room than a full-length insole, and thus may be employed more easily in some types of footwear, such as a thin, low-profile women's dress shoe. Although a moderator is not specifically illustrated in Fig 19, it is to be understood that one, optionally in the shape of a PED, preferably overlies each of the PEDs 430 and 431 to more uniformly distribute the loads imposed by the inflated PEDs across the ball and heel portions of the wearer's foot. In the embodiment of Figs 20 and 20A, an inflated insert or insole 530, like the embodiment shown in Fig 17 and 18, includes 2 layers 540 and 542 of barrier material, e.g., polyurethane, welded together at a plurality of circular areas, 546, 546. 546. The circular weld areas, 146, are arranged in a square pattern with each of the weld areas, 546, forming one corner of a square. When there is no load on the insole 530, e.g. when the wearer is seated, there are 4 points of contact, 545, 545, 545 of the inflated insole with the overlying ventilated moderator and the underlying sole 62 of the footwear in which the insole construction is incorporated. Comparing the embodiments of the inflated insole of the present invention shown in Figs 17 and 20, the inflated insole 530 provides a softer, floating-on-air sensation to the user because the intercommunicating pneumatic chambers in the insole are somewhat fewer and further apart. The inflated insole 330 shown in Fig 17 is somewhat firmer than the insole 530 disclosed in Fig 20. In the insert on insole 630 illustrated in Fig 23, 2 layers of barrier material, e.g. polyurethane, are welded together along weld lines 646, 646, 646 in the rear portion of the insole, 630, and at spaced weld areas 648, 648, 648 in the forward portion of the insole. Thus, the inflated insole 630 represents a combination of the weld pattern shown in the Fig 1 embodiment and the weld pattern shown in the Fig 17 embodiment. As a result, the insole 630 will provide different supportive characteristics under the ball and toe areas of the foot as compared to the heel and arch areas of the foot. Although not specifically shown in Fig 23, it is contemplated that the inflated insole 630 will be provided with a ventilated moderator 32 FIG2 overlying the inflated insole 630 to more uniformly distribute the load imposed by the inflated insole 630 across the plantar surface of the wearer's foot. In the embodiment of Fig 21, an inflated insert or insole 730 is disclosed which is similar to the Fig 17 embodiment. 2 layers of material are welded together at a multiplicity of circular weld areas 746, 746, 7A46. The weld areas 746 being arranged in a pattern of triangles, with each weld area forming an apex of an equilateral triangle. However, in the Fig 21 insole 730, the distances between the weld areas 746 vary. The distance between the weld areas 746 in the forward portion of the insole underlying the toes and the ball of the foot of the wearer are relatively close together, while the weld areas 746 in the rear portion of the insole underlying the heel of the wearer are spaced further apart. As a result of the varying spacing of the weld areas 746, the insole 730 will be thicker in the heel portion, where the weld areas are spaced further apart, and thinner in the toe portion, where the weld areas 746 are closer together. Moreover, because the spacing between the weld areas 746 is progressively less than region to region along the length of the insole 730, there is a smooth taper in the thickness of the insole from the rear of the insole to the forward portion thereof. Thus, the insole 730 is thicker in the heel area, i.e., the rear portion, where greater shock-absorbing characteristics are desired than in the front, where a more firm support is desired. In Fig 21, the end of a hypodermic needle 731 is shown in phantom lines as a means for inflating the insole 730. In Fig 22, an inflated insert, or insole 830, like the insole 730 shown in Fig 21, is designed to be thicker in the rear or heel portion than in the forward portion, to provide greater shock-absorbing characteristics in the heel portion and a more firm support in the forward portion, which underlies the ball and toes of the wearer's foot. This is accomplished by providing varying sizes of weld areas, 846, 846, 846, with uniform center-to-center spacing between the centers of the weld areas. The weld areas 846 located in the forward portion of the insole are relatively large, while the weld areas 846 in the rear or heel portion of the insole are comparatively small. As a result, the forward portion of the insole will be thinner and provide a more firm support and a softer pneumatic cushion, while the rear or heel portion of the insole will be thicker to provide greater shock-absorbing characteristics. It will be noted that the insole 830 has its weld areas 846 arranged in square patterns, with each weld area forming the corner of a square, similar to the embodiment shown in Fig 20. As is the case with all embodiments of the inflated insole construction previously described, the insole 830 is designed to be used in conjunction with a ventilated moderator 32, which overlies the insole to more evenly distribute the forces associated with the inflated insole 830 across the plantar surface of the foot of the wearer. Figs 24 to 26, inclusive, illustrate another inflated insole 30A that comprise two layers 40A, 42A of an elastomeric material of a type heretofore referred to, having its outer perimeter conforming to the desired shape for appropriate reception within a person's shoe. The periphery of the insole is determined by the weld line 44A, and the tubular chambers 50A, 50B are formed in the same general manner as described above in connection with Fig 1 by the spaced weld lines 46A, 46B, 46C, the tubular chambers being connected to an intermediate tubular section 58A, curving around the rear portion of the inflated insole. The forward weld lines 46B, 46C are of a generally herringbone pattern, as illustrated, to provide tubular chambers 50BB of generally zigzag shape. The rear set of weld lines 46B have terminal points 54AA spaced from opposed terminal points 56A of the herringbone pattern weld lines 46C that extend under the toe portion of the foot. The space is 55A between the terminal opposed terminal points. 54A, 56A provide openings or passages between adjacent tubular portions, permitting intercommunication between all of the chambers in the insole in essentially the same manner as disclosed in Fig 1. In use, a suitable motor Artor 32 will overlie the insole 30A. The insoles disclosed in Phi-B the spaced weld lines 46A, 46B, 46C, the tubular chambers being connected to an intermediate tubular section, 58A, curving around the rear portion of the inflated insole. The forward weld lines 46B, 46C are of a generally herringbone pattern, as illustrated, to provide tubular chambers 50BB of generally zigzag shape. The rear set of weld lines 46B have terminal points 54AA spaced from opposed terminal points 56A of the herringbone pattern weld lines 46C that extend under the toe portion of the foot. The spaces 55A between the terminal opposed terminal points 54A, 56A provide openings or passages between adjacent tubular portions, permitting intercommunication between all of the chambers in the insole in essentially the same manner as disclosed in Fig 1. In use, a suitable moderator 32 will overlie the insole 30A. The insoles disclosed in Figs 1, 15, and 16 tend to curl slightly when properly inflated. This tendency has little importance when the insole is removably mounted within a shoe. However, it is preferred to have an insole that lies substantially flat when permanently attached in the shoe. In the form of invention illustrated in Fig 23, The spaced weld areas or dots 648 in the forward portion of the insole result in the insole lying flat and reduces the tendency of the tubular chambered portions 50 to curl. The reduced curling tendency enables the insole to be mounted readily in the shoe. However, the space weld areas 648 may not be capable of withstanding the repeated stresses to which they are subjected over substantial periods of time, resulting in failure at some of the weld areas.
Having trouble sleeping? Let us read you some bedtime stories guaranteed to put you right to sound slumber. We are reading selected patents on a variety of inventions, past and present. While you're falling asleep, you will subconsciously gain knowledge and insight on inventions that advanced our technology in many technical areas and industries. What more could you ask for? Sleepy Time for Nerds is perfect for engineers, scientists, physicists, and the weekend tinkerer. Sleep tight.